All right, welcome back everyone to Psych 3510 for part 2 of our single sample t-test lecture. In the last video, we learned just sort of about the test itself, when we use it, why it exists, how to calculate it, and then how to make a significance decision and write up an APA-style conclusion for a single sample t-test. In this part, we're going to dive a little bit more into this whole issue of a one-tailed versus a two-tailed test. We'll talk about why that exists and why it impacts us and our decision making. And then we'll get into some practice problems for the end of the lecture. So if you remember from last time, a one-tailed hypothesis is a hypothesis that makes a specific prediction about directionality. We have to determine whether a hypothesis contains directionality by the language in the research question, specifically the language in the hypothesis. So do we think that a group will be less than, greater than, more than, faster than, slower than, smarter than, right, meaner than, whatever the variable is the researcher making a prediction that the group will score less than or that the group will score greater than the population of interest for comparison? So what happens when we have a one-tailed hypothesis is that we're setting up our critical value on one side of the curve. Here we have, let me get my laser pointer. Here we have a one-tailed positive hypothesis because we're on the right-hand side of the curve above the mean. Let's just say that this is our critical value, whatever it is. And if our alpha is 0.05, then what that 0.05 means is that this critical value, our benchmark, our hurdle, is the point on the curve that 5% of cases are more extreme than. This is where all that work with z-tests and the z-table really come back to be important conceptually. We're working here, of course, with t-tests, but it's the same idea. We can find a place on the curve where 5% of cases of people are more extreme than that point. And when we say that alpha is 0.05, what we're saying as scientists is we're saying that we will be convinced by a finding that is in the top 5% most extreme of our scores. That for us to consider our, in this case for a t-test, for us to consider our group to be different from the population, our group must fall in the 5% most extreme area of the curve. That's what alpha equals 0.05 means. And using alpha equals 0.05 to find our critical value finds us that exact place on the curve, our line in the sand, where 5% of people are above it in this case, and 95% of people are below it. So this is our marker of extremity. If alpha was 0.01, then this would be the place. It would be further over in the curve, right? It would be over here because 1% is more extreme. If our alpha was 0.01, then it would be the place on the curve where 1% of individuals are above it and 99% of individuals are below it. And what we would be saying as scientists is that we will only be convinced by a score that is so extreme that it represents 1% or less of the population. Now, if we make a non-specific prediction without directionality, we have a two-tailed hypothesis. We call it tails because what we're looking for is area in the tail of the curve. So we have a non-specific two-tailed hypothesis, meaning the language of our hypothesis is non-directional. So our sample will deviate from, will differ from, will not be equal to, right? These terms don't convey above or below, less, more. They don't convey directionality. The term deviate from or different from simply could mean less than, or it could mean greater than. So what that means is that we're doing what's probably called an exploratory analysis. We don't have a good a good reason to hypothesize that this group will be less than or that the group will be greater than the population. We're not sure. We just think they will differ. Well, if we're going to give ourselves both sides of the curve, then if alpha is 0.05, both sides of the curve can't contain 5% of the population, because that would be 5% plus 5%, which would be alpha would actually be 0.10. We would be giving ourselves a 10% of the population chance to be significant. So what we have to do is cut alpha in half, essentially, and distribute half of alpha's probability above on the high side of the curve and half of alpha's probability on the low side of the curve, such that if alpha is 0.05, you have a point for our critical value where 2.5% of the population is above, and then a point on the low end where 2.5% of the population is below. So we have two critical values, each which draw a line in the sand for 2.5% of the most extreme population, 2.5% below, 2.5% above, which combine to become our alpha of 5%, 0.05. And so we would have to do the same thing if alpha is 0.01. If alpha is 1%, then we have to distribute half of alpha on the high side and half of alpha on the low side, meaning that we are only convinced if our sample falls in the 0.5% most extreme below or 0.5 most extreme above percent of the population. So because a two-tailed test allows us to reject the null on either side, what ends up happening in a two-tailed test is that our critical values move out on the curve, right, to accommodate for the fact that percentages get distributed on both sides. So imagine that we have a one-tailed hypothesis that athletes will bench press more than the average student, meaning, well, we set up some critical value here with degrees of freedom 10 and alpha of 0.05. A critical value is 1.812. So athletes will bench press more, meaning we will be convinced if our athletes fall in the top 5% of bench press weight. Now, if we were to do this in a two-tailed manner, we would have to change our hypothesis language, right? Our hypothesis would be different. It would be that athletes will bench press a different amount than the average student. Then what ends up happening if we go look at our t-table, and I suggest that you do look at the t-table here, what ends up happening with degrees of freedom 10, alpha is 0.05, with a two-tailed test, our critical value becomes plus or minus 2.228. So notice how the t critical goes from 1.812 with a one-tailed test to 2.228. It moves out in the curve, which makes it more difficult. But we're making it more difficult because we get both sides of the curve. We get essentially two chances to be significant. We get a chance on the low end and a chance on the high end. And so we distribute 2.5% of my probability, half of my alpha of 0.05 on the high end, and then the other half of my alpha on the low end, such that now the total probability of statistical significance is still 5%, because that's what we need it to be, because alpha was 0.05. So let's work on identifying hypotheses. And there are three types of hypotheses you need to be able to identify: a one-tailed positive, a one-tailed negative, or a two-tailed hypothesis. So here we have, it looks like 5 examples of possible hypotheses. I want you to press pause and take a minute to consider each of these hypotheses in turn and determine whether it's a one-tailed positive, one-tailed negative, or two-tailed. Then hit play and we'll reveal the answers. So go ahead and hit pause and do that now. All right, hopefully you're back. And let's go through our answers. Do 8-year-olds cry more than 10-year-olds? The key here is more than. So we have a one-tailed hypothesis. Do people from New York City differ in the number of curse words they use than people from Atlanta? Our key directionality language, or in this case, lack of directionality language, is differ from. So we have a two-tailed hypothesis. We don't know whether they're going to be less than or greater than. Does the medication increase side effects? Keyword here is increase, one-tailed positive. Does mindfulness meditation reduce scores on a measure of anxiety? We have reduce, so that's our one-tailed negative. And do Boston Terriers have different lifespans than German Shepherds? We have our non-directional word and language different, so we have a two-tailed hypothesis. Now, you're going to need to be able to do this on your own in examples, because this distinction between a one-tailed positive, one-tailed negative, and two-tailed test is going to tell you what your critical value needs to be. If you have a one-tailed positive test, then you're just taking the critical value that's on the table. If you have a one-tailed negative test, you're taking the critical value on the table and you're putting a negative sign in front of it. If you have a two-tailed test, you're taking the critical value and you're saying plus or minus that value, because you're going to put a benchmark, a hurdle, a line in the sand with your critical value on the high end and the low end of the distribution. Okay, so let's do another practice problem. What I actually want you to do is, again, hit pause, and I want you to see if you can go through this entire problem all by yourself, and then come back and check on your answers. So remember, you're going to need to define your hypotheses. You're going to need to calculate your standard deviation of your sample. You're going to need to then calculate your t-value. You're going to need to use alpha and your hypothesis directionality and your degrees of freedom in order to calculate a critical value. Then you're going to need to compare your calculated t-value to your critical value. If you're significant, then you need to perform an effect size. And then I want you to write up an APA-style hypothesis. So go ahead and hit pause, and then come back and hit play when you're ready to check your answers and watch my walkthrough. Okay, so in this example, you study media consumption in families, and you want to know if stay-at-home parents watch a different amount of television than the average adult. You know that on average, adults watch 3.5 hours of television per day. That's our population mean. That's our given. We just know that that's the case. But we don't have the standard deviation for that value, for that population. So what we do is we collect data from 6 stay-at-home parents, and we ask them, or maybe we assess somehow, how much they watch TV per day. Using the data below and assuming that alpha is 0.01, do stay-at-home parents watch a different amount of TV than the average adult? So here we have a two-tailed hypothesis because we say different amount of TV. Our alpha is 0.01. Our N is 6, which means we'll have 5 degrees of freedom. Our population mean is 3.5. And then we're going to use our raw data to calculate a sample mean and a sample standard deviation to round out our t-test. So first step, our hypotheses. When we have a non-directional hypothesis, a two-tailed hypothesis, that means we're saying that they will be different from. We don't know whether they'll be less than or greater than, just different from. So our research hypothesis, our H1, is that stay-at-home parents are not equal to the average adult, right? We want to know, do they differ from the average adult? So are stay-at-home parents different from, right, not equal to the average adult? And so our null hypothesis is that stay-at-home parents will in fact be equal to the average adult. So when you have a one-tailed hypothesis, you're going to have inequalities, right? You're going to have greater than, less than, greater than or equal to, less than or equal to. In a two-tailed hypothesis, you will always have not equal to and equal to, right? Because this not equal covers both the low end and the high end. Okay, so first step is calculating our sum of squares, our sample variance, and our sample standard deviation. Here we have our raw data. our 6 adults and the number of hours they watch television. Turns out that they average exactly 3 hours of television per day. We find our deviance scores from the mean. We square our deviances. We add up those square deviances to give me a sum of squares of 8. We then take that sum of squares and we plop it into our sample variance formula, which is sum of squares divided by n minus 1. So 8 divided by what will become 5, because I had 6 participants. 8 divided by 5 is 1.6. 1.6 is our sample variance, s squared. I need s for my t-test. So I take 1.6 and I take its square root, and it gives me 1.26. So now I actually have everything I need for the t-test. I have my sample mean over here that I found for my sum of squares of 3. I have my sample standard deviation, 1.26. I have my n, which was 6. And the population mean was given to us. I believe that was 3.5. Yes, 3.5. So we have everything we need to calculate our t-test. We plug and chug. We put the 3 over here in x bar minus our population mean of 3.5 divided by our sample standard deviation 1.26, which is divided by the square root of n, which is 6. The square root of 6 is 2.45. 1.26 divided by 2.45 is 0.51. 3 minus 3.5 is negative 0.5. Remember that negative is important. It tells us which side of the curve we're on. Negative 0.5 divided by 0.51 is just shy of negative 1. Negative 0.98 is our critical t-value. Not looking too good. Doesn't look like we're going to be significant, but we have to check with our critical value. Right? We have to check the critical value table and compare it to this calculated t. So we do that here. We need our 3 pieces of information: degrees of freedom, n minus 1, alpha, which was 0.01, and then our decision about whether this was a one-tailed or a two-tailed test. If you get this decision wrong, 1 versus two-tailed, then you will get the incorrect critical value. N minus 1 is 5, right? 6 minus 1. Alpha was given in the problem. That's 0.01. And we determined, because we had non-directional language in our hypothesis, that we have a two-tailed test. So degrees of freedom 5, we know we're working on this row. Two-tailed test. So we need to use this row to find our alpha of 0.01. So we're right there. So we're using this column. We see where the column and the row intersect, and it gives us a critical value of plus or minus 4.032. Don't forget that this is plus or minus because we have a two-tailed test. And so we will be putting 4.032 as a critical value both above and below the mean on our comparison distribution. So our critical t-values are way out here, right? Plus or minus 4.032. Our calculated t, our sample, the t we derived from our sample, is negative 0.98. We're right here. So our calculated t did not cross over either of our thresholds. We are not more extreme. What this tells us is that our stay-at-home parents are equal to the average adult, everyone else, right? We are too close to the mean for us to conclude that they're different from the average adult. They are effectively the same as the average adult. They are not more extreme than the cutoff. They're too close to the mean. We fail to reject the null, so we're holding on to the null. We're keeping the null. And the null was that they do not differ, right? They are equal to the average adult. Now, because we failed to reject the null, because we were not statistically significant, we do not need to calculate an effect size. We don't need to know the size of the effect because there was no effect. If there is no effect, then its magnitude is irrelevant. We don't need it. Just ignore step 6, ignore the effect size if you are not significant. If the t-test is not significant, meaning we fail to reject the null, then you ignore the effect size. If the t-test is significant, then we need to calculate the effect size. So we can move straight on to our APA-style conclusion. A single sample t-test was conducted. Whoops, sorry about that. A single sample t-test was conducted to see if stay-at-home parents differ from the average adult and how much they watch TV. So we did part 1. We introduced the test, and we introduced our research question and hypothesis. We failed to reject the null. No significant difference was found between stay-at-home parents, who were our sample, don't forget, our sample of 6 stay-at-home parents who had a mean of 3 hours of TV per day, a standard deviation of 1.26, and the average adult, who was our population comparison mean, which was 3.5. So we told our reader whether we failed to reject or rejected the null. We failed to reject, so there's no significant difference. Then we provided our 2 groups, our sample, our experimental sample, and the people that we were comparing them to with the descriptive statistics for each. We calculated our mean and we calculated the standard deviation from our raw data with our stay-at-home parents. And then our average adult, the population, was given to us. Now we need our statistical t statement, t, parentheses, degrees of freedom, 5, which is n-1, equals our calculated t, negative 0.98. We don't have a Cohen's d, so we just drop it and ignore it. And we were not significant, so n.s. And now we need to provide our take-home message. So thus, stay-at-home parents do not differ from the average adult in the amount of TV that they watch. Now, I want to make one important point about this. That first, the next couple of slides are practice problems, specifically 3 practice problems. The answers to these practice problems are posted on iCollege. You can access them and check your answers. I won't be providing a voiceover for those, but the step-by-step answers are all there for you to take a look at. But practice problem number 1 makes an important point, which is that you need to be able to conduct this test from summary data as well as from raw data. Now, what raw data means is that you are given the individual scores of your sample. So this last example about television watching, you were given the individual scores of your sample, right? Each of these numbers represents a single person. And we had to use their individual data to calculate a mean, which let us calculate a sum of squares, which let us calculate S, right, the standard deviation of the sample that we need for the t-test. If I give you summary data, what it means is that I'll just give all of this to you to begin with. You will not have to do the sum of squares table. I will just give you their mean, and I will give you the sample standard deviation, and then you can just pick it up from there, right? So we can sort of cut out the middleman of the sum of squares. It's possible that on the exam I would do that. So you need to know how to calculate it like this, what you see here from raw data. And then here's a practice problem where you calculate it from summary data. So you're a developmental psychologist who wants to know if 6th graders in a special reading program have higher scores than the average 6th grader. So our special reading program is going to be our sample, and we're comparing them to the population of average 6th graders. The average 6th grader scores a 55, so that's our population mean. You collect data from 25, that's N, 6th graders, with a mean of 78, so I give you the sample mean, and a standard deviation of 4. I'm giving you the sample standard deviation. So I'm just giving you a bit of a head start. You don't have to do that math on the sum of squares table. You can just pick up directly from the t-test. So your first example is from summary data, and then examples 2 and 3 are from raw data, like the other examples in the lecture. So take a look at these practice problems. Make sure you work on them. Make sure you look up the correct answers in iCollege. and this will be it before the exam. So good luck on the exam. Take a look at all the materials in iCollege from single sample t-test and the previous topics that will be covered in this exam. And please let me know if you have any questions. Thanks, everybody, and I will talk to you later.